The alkylation of a terminal alkyne. So, as the name of this reaction implies, we start with an alkyne that is terminal, that is to say at the end of the chain. And ultimately what we are adding is an alkyl group. So we're going to replace this hydrogen with another R group in this reaction. And so I will indicate R prime just to differentiate these two R groups. So how this reaction works is we need to first remove this hydrogen atom at the end of the alkyne. So we can do that by treating it with a strong base. So the strong base that is commonly used for this reaction is Na, NH2, or sodium amide. So if we recall from an earlier chapter on acidity, the pKa of an alkyne proton is around 25. So to remove that, we need a base that is stronger than the anion that we will form after it's removed. So that means we need a base whose conjugate acid has a pKa greater than 25. The base we are using here, NH2. So there's NH2 minus. So we are using this base to remove this hydrogen and push the electrons onto here. So what we are forming is ammonia, NH3. And ammonia, the conjugate acid of this NH2 minus, has a pKa of around 38, meaning that this NH2 minus is a stronger base than the ion that we form, and so this acid-base equilibrium will be favorable. After we form this ion, this is known as an acetylide ion. This is a powerful nucleophile, and if we want to add an alkyl group, that means we need a carbon atom that is electrophilic. And so the way that we do this in a second step is we would add that R group, and to make it electrophilic, we would make sure that it has a bond to an electronegative atom. So if we were to add, say, our R group attached to chlorine, chlorine is electrophilic, and what would happen is these electrons would attack the carbon that is attached to that chlorine, and the bond between the carbon and the chlorine would break. We need to know a few more important details about this reaction, such as some restrictions on that alkyl halide. So the alkyl halide that we use for this reaction must be relatively unhindered. So it must be either a methyl halide So I'm calling this unhindered because the carbon attached to the halogen only has bonds to 3 small hydrogen atoms. It could also be one where we replaced one of these hydrogen atoms with a carbon. And so what we would call that sort of halide, a carbon with one bond to other carbons, is a primary carbon, so this is a primary halide. If we were to try to use a different halide, something more substituted than a primary halide, we would end up with a competing reaction taking place, and we will talk about that reaction when we get to chapter 9. Let's look at some specific examples here. So I'm going to fill in some R groups with some carbon atoms. So if I start with this terminal alkyne, I have 1, 2, 3, 4, 5 carbon atoms. And if I treat this first with sodium amide, and then I use a methyl halide, such as methyl iodide, what I will do is I will end up adding the methyl group to carbon 1. And so the product of this reaction would have the 5 carbon atoms that we started with, plus a methyl group now added to that end carbon. So, and then we have an extra carbon. And that extra carbon came from the methyl iodide. Let's look at another example. So here is another terminal alkyne. This time we have 1, 2, 3, 4, 5, 6 carbon atoms. If I treat this first with sodium amide, NaNH2, and this time I'll use a primary halide. I'll just make that R group a methyl. So this will be an ethyl halide. So I'll use ethyl bromide. And so in this reaction, we will be adding 2 carbon atoms right here. So we're starting with a 6 carbon atom chain. If we add 2 more carbon atoms, we should have an 8 carbon atom chain. So 1, 2. So here are the 6 carbon atoms that we started with. And here are the 2 new carbon atoms. So it is this carbon, the one that's attached to the halogen, that is right here, the CH2, and then the CH3 at the end of the chain.